minutes more.
Yeah.
Sorry.
Okay. Yeah.
One,
I'll
one, and
switch.
two, yeah. How was the how was the safety there?
Yeah.
I heard some news.
Yeah. Okay. Luckily in UAE, everything is silent.
Silent? Okay, nice. So I hope you safe there. 2 minutes.
Okay. I'll switch off sound and video and then switch it on when we'll start.
Okay. Oh, oh, I see. So let's begin the colloquium. Thank you for everyone to joining us. Good afternoon to all participants. Welcome to Brain Quantum Physics Colloquium. My name is Joko Swardi. I'm a researcher in the Research Center of Quantum Physics, Brain. Today I will serving as a moderator for today colloquium. For your information, we basically organize our quantum physics colloquium 2 times every month. We invite the speakers not only from our research center, but also the guest speaker from other institutions. For today, we are pleased to have Dr. Yury Kurochkin as our guest speaker from Technology Innovation Institute, Abu Dhabi, a leading global research center, part of Abu Dhabi government's Advanced Technology Research and Council, which oversees the technology research in Emirates. Dr. Kurochkin will speak about quantum communications, connecting the quantum world with practical application. It's my pleasure to welcome Dr. Kurochkin. Before we start, please allow me to briefly introduce our speaker. Dr. Kurochkin received his bachelor degree in physics in 2006, master's in 2007, and a PhD in 2012 from Moscow Institute of Physics and Technology, one of
Correct.
the Russian leading institute in science and engineering. He began his research career as a postdoctoral fellow at a Russian Quantum Center from 2012 until 2015. He focused on experimental studies in quantum optics. From 2015 to 2022, he led the quantum communication group at the same institution, overseeing the development of quantum key distribution or QKD, designed for industrial application. Since 2022, Dr. Kurochkin has been with the Technology Innovation Institute in Abu Dhabi. He served as a lead researcher for 3 years and currently holds the position of a principal investigator. So with that, Dr. Kurochkin, you have 1 hour for the presentation and 30 minutes for a question and answer. Please be
Okay.
informed to all participants, if you have any question during the presentation, please post your question in the chat. And then Dr. Kurochkin, if any question appear in the middle of your presentation, please ignore that. I will read it after your presentation is finished. So if so, Dr. Kurochkin, the floor is yours. Yeah.
Okay. Thank you. Thank you. So, yeah, again, few words about Technology Innovation Institute. Its mission is to transform UAE economy from resource-based to knowledge-based, and it covers highest priority directions of research, so that it works not only on quantum technologies. There are around 1,000 researchers in TI and 9 research center. So apart from quantum, there is AI, robotics, materials, and others. And in quantum research center, which is around 100 employees, there are more or less canonical quantum computers, quantum communications, and quantum sensors on the experimental side. And there are a number of 3 theoretical groups: quantum algorithms, quantum physics, and quantum middleware, mainly focused to support quantum computers, which is like most resourceful application. But today I will speak mainly about my favorite, quantum communications, which is nowadays I think they're the closest to the industry part of quantum technologies. So as soon as we talk about communications, and in particular secure communications, let's first have a hint about the problem statement. And the problem is following: it's very hard to keep your data secure for a long time. So people have invented different methods of encryptions like thousands years ago, and there is always competition between encryption and decryption capability. And if, for example, you store your encrypted data for a long time, at some point somebody can invent a new approach, decrypt it, and access your data. And for last, let's say 50 years, people have been using mainly asymmetric cryptography, which is really threatened by quantum computers. So about 80% of today's cryptographic infrastructure is under quantum computer threat. And recent developments in laboratories, startups, and companies like Google, IBM, Microsoft, all over the globe, has demonstrated there is a time to be worried. And that's not only like information from people who are doing quantum technologies, but also from the standardization agencies, which urge companies to find quantum secure solutions. But let's see, like, did it appear really as an unexpected event or not? So if you look at the history, we found out that actually quantum computer was first proposed by Richard Feynman in the early 80s. But initial idea of quantum computer was actually to model quantum physics, quantum processes, not by classical computer, but by quantum computer. And it's still the highest priority task of quantum computers, because it's very hard to model complicated materials on the quantum level. It's hard to model drugs on the quantum level. So let's say how will protein inside in a medicine will act on a let's say a cell membrane, and that's a main locomotive of quantum computing industry. At the same time, in 1994, so that's more than 30 years ago, Peter Shor proposed an algorithm which is breaking an asymmetric cryptography like RSA and Diffie-Hellman based on prime number multiplication factorization problem. And many people will surprise why industry and regulation agencies are urging people to migrate only now, not in early 90s. And the answer is very simple. So back then, in 90s, quantum computers were somewhat like a beautiful concept. And only now they're becoming mature enough to make this threat to be a foreseeable factor. But if we look at the quantum communications, the quantum communications concept was proposed even prior to quantum computers. So Weisner's quantum money concept was proposed even before quantum computer. So idea of quantum money is to make an unforgeable money based on the quantum properties. That's still in practical protocol. But in 1984 was first proposed first practical quantum protocol, and that's PB84 protocol, named of the for these two gentlemen, Bennett and Brassard. And it's still the most popular quantum communication protocol now. So let's have a deep dive into how like encryption decryption problem is stated. So to encrypt data, you need a key. Even if you are using that's one of the first encryption protocols, the Caesar cipher. When you move your alphabet, let's say 3 steps forward or like 20 steps forward, the key is number of letters you are moving your alphabet. So you need to send a key to the exchange a key between receiver and transmitter. And only then you can encrypt, send, and decrypt data. But the problem of classical information is that you can make unlimited number of copies of the information without disturbing it. Actually, that's a blessing property of classical information. That's why all internet is working, because when we are sending some files, of course, the errors can occur during the transmission, but we can easily put redundancy and put error correction codes. That's why all our files are stored with a good quality. But that also means that an adversary can monitor your communication channels and make copy both of your public of your encrypted data and key agreement protocol. Of course, let's say RSA and Diffie-Hellman claims that all mathematicians who tried to solve this problem found only exponentially hard solution, except Peter Shor. So that means that when quantum computer will be available, an adversary can use key agreement information to resolve the private key, decrypt data, and have access to whole secrets. So that's why a quantum computer's progress has so large impact on the information security area. And many people say that there is still no available powerful enough quantum computer. But we have a time competition, and there is so-called inequality, which says the following. Let's say we have a task of a quantum computer to be done. And that's some kind of expert estimation time. At the same time, we have a forecast of how much time do we need to migrate our information security infrastructure. And we also have time which we want our data to be secure. So as soon as migration happens gradually, we need to add the 2 times, migration time and data security time. And migration time, according to, let's say, NIST, is something like, it says that around 2030, all entities should, like at least in the United States, should migrate to quantum secure solutions. But if you want your data to be secure, let's say for 10 years, then you need to have that your time horizon is something like 2040. And if we have a reasonable probability to quantum computer to be done before that, then that's real a worry, like call for action. And according to the actions of all all regulators, this inequality is already fulfilled, and it's time to do something. So personally, I like to protect quantum against quantum attacks using quantum mechanics. And the good thing about the quantum states is that unlike the classical information, you cannot make exact copies of quantum information. So that means that even if you make an ideal noiseless quantum copy machine, which can work on the limits, which is limited only by quantum mechanics laws, it will not provide you with an ideal copy of quantum state. And at the same time, it will affect an initial quantum state. So like in classical analogy, you put a paper in your copy machine, make a copy, and you have like not very good copy first. Then you look at your initial paper and you see that it's, let's say, burned a little bit. So that's how quantum copy machine works. And it's easy to imagine, like, let's say you have an atom in a trap, and your photon, which carrying information, is passing by your atom. And with some like cavity interaction between atom and photon, part of information from about your photon goes on the atom. So photon changes the state of the atom. At the same time, not only photon affects atom, but there is a back action, atom affects photon. And photon is no longer the same. So let's go here. So in classical, we can have many ideal copies. In quantum, even if we have one copy, it's non-ideal and your initial state is changed. So that means that we can use quantum states, states of single photons, to send a key, an encryption key. And if somebody will try to measure your quantum key and reveal some information, you will see it as a bit error rate, and you will see that your key was attacked. And if your key cannot be trusted, you just don't use it. You didn't send useful information before. But if it passes all tests, then you can use it for data encryption. So that's how the BB84 protocol works. So Alice transmitter chooses random bits of the key to send and chooses random bases. What's a basis? Basis, let's say in polarization domain, it encrypts logical 0 and 1 with vertical and horizontal polarization, and in another basis, rotated 45 degree, 0 and 1, is encoded with anti-diagonal and diagonal polarization. So with random choice of bit and basis, Alice chooses between 4 states of single photon: diagonal, horizontal, vertical, diagonal, anti-diagonal, and send it to the receiver. Receiver, which is usually called Bob, do not know anything about bit or basis chosen, but Alice. So what can Bob do? Bob can randomly try to guess basis. So Bob randomly chooses a basis, is it vertical, horizontal, or diagonal, and make measurements. And if basis of the Bob coincides, Bob has correlated bit with Alice. If bases do not coincide, Bob has completely random outcome. But remember that Alice is sending just random non-correlated bit sequence. So what can Alice and Bob do? They can just announce basis which was used and discard events when bases did not coincide. So in their bit sequence, a key sequence, they will remain only correlated events when bases and bits coincided. But what if eavesdropper is in place? So Alice, let's choose one state of Alice. Like for other states, it will be the same. So Alice, let's say, prepare vertical polarization. And Eve, which is called eavesdropper, called Eve, do not know anything about the basis, so she has to guess. And in 50% of cases, Alice's guess was correct. And the state is completely the same. So in 50% of cases, Eve did not disturb the state. So it measures correct state and resends the same state. But in 50% cases, the measurement basis was wrong. And the outcome was random. And that means that on the Bob side, in case Bob and we consider only events when Alice and Bob bases coincided. So if Bob measures diagonal or anti-diagonal states in a vertical horizontal basis, outcome would be random. So that means that in 50 of the 50, like quarter percent, like in 25% of states, Bob will have a bit flip. So the quantum bit error rate, that's an error rate which was observed by receiver, will be 25%. And it's easy to we can calculate that mutual information between Alice and Eve in this case is double quantum bit error rate. And yes, if you see 25% of errors, you cannot have a good you cannot distill a quantum key. As I mentioned before, an eavesdropper, we should consider an ideal quantum copy machine, which is limited only by quantum mechanics laws. So you see this linear part, which is here. It was calculated only intercept-resent strategy, but there are more optimal strategies which include weak measurement. This red line, that's mutual information between Alice and Eve, and the black line which goes down, it's actually information between Alice and Bob, and it goes down with error increase. So the possible secret key rate is this gap between information between Alice and Eve and information between Alice and Bob, and it goes to zero around 15%. But you also need to correct errors. So it was it was shown mathematically that there are efficient distillation protocols which can give you non-zero key generation up to 11%, and between 11 and 15%, there is a possibility to have quantum key, but there is no efficient protocol. So usually we are considering that we can, in principle, generate quantum key only if error rate is below 11%. So it actually means that Alice manifests its presence by error rate. And let's assemble it from a theoretical concept proposed 40 years, okay, already 41 years ago, to some practical application. So what can we do? We can make two devices called Alice and Bob. Photons are going from Alice to Bob, and then Alice and Bob generate symmetric key. If it was attempt to measure the key, they discard the key. If key error rate is below 11%, they can perform error correction and privacy amplification protocol to remove eavesdroppers information, and then upload quantum keys to user devices. So usually this user devices is not something completely abstract, but there are L1, L2, or L3 high-speed encryptors, which use AES protocol, which is believed to be safe against quantum computers. But usually it consumes keys from Diffie-Hellman or RSA, and we add quantum keys to make this solution quantum secure. So there is very good news for industry. It means that it should not rebuild its information security infrastructure, but it should amend it with quantum secure keys and upload it to applications. So maybe you heard about the letters, the position papers about quantum key distributions. There are two of them, one from United States and another from European agency, like in United States, that's NSA. In Europe, that's German BSI, also French and Netherlands agencies. And they say that quantum key distribution has a number of weaknesses, and they urge to use post-quantum cryptography instead. So first of all, like for people who are doing quantum key distribution, it's not a weaknesses of QKD, it's actually a to-do list for QKD. And let's say, like there are a few of them. One of them is that equipment is too expensive, for example. Another is that it requires trusted nodes to send longer distances, or there is need of certification, but actually you need to certify both quantum and post-quantum. So luckily, not only QKD community, but a classical cryptography community has proposed beautiful solutions. So for example, the company called Actron, former ADVA, has incorporated in their encryptors a way to use quantum keys. But if you look inside the box, you will see that they mix keys, they use three types of keys inside. They use Diffie-Hellman, which is vulnerable to quantum computer, but well tested. They use post-quantum, which believed to be secure against against the Shor algorithm, but nobody knows if there exists or not exist efficient, even classical algorithm to hack. And there is a QKD, quantum key distribution, which is much more expensive because it's hardware. But the good thing is that it has information theoretical proof of key distribution. So it claims that if somebody who wants to make an attack is capable to everything what is not prohibited by laws of physics, including unlimited computational power, it's impossible to get the quantum key. And there are good examples of the QKD and PQC of coexistence. For example, an SK Telecom, Korean company who adopted a lot of QKD devices, especially for 5G communication. So they combine QKD to connect node data centers or connect 5G base stations, and then they connect locally the devices or smartphones using PQC. So when you have large flow of data aggregated from different users, it's protected by QKD. If you have a connection only to particular user where risks are less severe, they use PQC. If you look in the implementation of QKD, we see that usually QKD is something point to point. So if you have many users in let's say in the city, we see here the picture of National Quantum Network in Singapore, we can organize so-called quantum network. So imagine in the city you have fully connected nodes of quantum network. Each one is connected with QKD lines. So we need to assume that they are connected with dedicated fiber channel. It's dark fiber. And but what if two nodes, let's say on the left picture on the green plane, A and B, do not have direct connection? They have a central node in between. So they have intermediate layer, so-called key management layer. In brief, like A and C have pair of keys and C and B have pair of keys. What can C do, node C do? It can use key between C and B to encrypt a key of node A and send it to node B, and A and B will have the same key. And usually it's used by the so-called one-time pad encryption. That's just bitwise sort. So on application layer, the users do not have to worry about the whole infrastructure beneath. They just receive a pair of symmetric keys. And in between, it's used not only quantum devices, but also it was tested between different encryptors, Thales HSMs, Hitachi Energy, or power grid orchestrated devices and others. So it's very well integrated in network stack infrastructure. So nowadays, a leader in quantum networks is China. It has around 5 million users. That's information about, let's say, a year ago. And a very broad quantum network connecting many cities. So first 4 cities which were connected in 2016 was Beijing, Shanghai, Hefei, and Jinan. Now have much more cities, and each city has their own quantum network. Europe has very large initiative called EuroQCI, which is progressing very quickly. Countries are building their local quantum networks, and there is also a big project to connect the national quantum networks between each other. Of course, the China has huge advantage of dense population because that you need to send photons in the fiber, and there are losses which are when you have a limit on the distance. So more population per square meter you have, easier to implement the economically viable quantum networks. So that's why regions like China is number one. Also, Singapore and South Korea are actively developing quantum networks. So very good example is disaster recovery, which is you can see on the if you want to see it, there is a quantum CTEC company which is one of the leaders in quantum communications. It has on the website they have a use cases described. So here I'll say that about disaster recovery. Disaster recovery is very important use case because company needs to, let's say, back up all its valuable information to remote center, and it's absolutely necessary to do because natural disasters like floods, earthquakes can demolish the data center, and nobody wants to lose all information. That's why you need to send it via the untrusted environment, and the quantum is the best solution. But there are a large number of other possible applications. For example, in my previous work, we made a first proposal of quantum secure blockchain. Now it's a whole big area of research. People are applying quantum keys to protect blockchain solutions. So we made it in like 2017. But I'm happy that last year JP Morgan also used quantum keys to protect blockchain solutions in the United States. So let's say in the second half of my talk about work we are doing in Technology Innovation Institute. We have a number of products and projects. So one of them is so-called entangled state quantum key distribution. So the QKD I described above with BB84 protocol, it's so-called prepare and measure QKD. When you prepare for state of the photon, send and measure. Entangled is a little bit different, I will say later. Also, we have so-called last mile quantum key distribution, which we want to address one of these issues of equipment cost problem identified both by NSA, BSI, but well, different agencies. We also have a quantum random number generator project, which I would say only a few words here. So it's if you want to make post-quantum cryptography, you still need randomness. And here in our team, we made so-called white box QRNG. If you look at the quantum random number generators available on the market now, all of them are black box. You need to trust what's inside. Our model of commercialization is to provide a royalty to self-production. So our ideal client is a manufacturer of some classical security equipment or laptop manufacturer. So we can provide a design of QKD to our client, and client can make a quantum random number generator using these all off-the-shelf components. And that's beautiful because there is a new level of trust. And there is also ground to satellite QKD to go to ultra-long distances to address the problem of the distance and the loss, which is also identified in this position letters. So let's talk a little bit about entangled QKD. It's absolutely beautiful science behind this, and it's called it was first proposed by Arthur Eckert, and then it was developed a modified protocol called BBM92. So idea is following: if you use entangled states photons, and to generate these photons, people usually use nonlinear optical crystals and SPDC process. You pump, let's say you pump it with a photon which has high energy, and it decays into two photons which has both of them has twice less energy, and you can make in a non-degenerate way. So one photon with slightly larger energy, one photon with slightly low energy. On the upper picture there is a diagram how the photons are generated depending on the temperature and the wavelengths. And in BBM92 protocol very much reminds BB84 protocol, but it says following. So instead of one receiver, there are two receivers, two users. Each of them receives a half of the entangled state. So that's HH plus VV, which horizontal plus vertical. HH means both photons horizontal, VV both vertical. But if you make a rotation of this state, so the diagonal is equal to sum of H plus V, and anti-diagonal is equal to H minus V. So you will see diagonal plus anti-diagonal. So two sides has entangled photons, and as soon as process is spontaneous, sometimes there can be two pairs instead of one, but that's not a problem, not a big problem, because it will, if participants will measure photons from different states, you will have just slightly more error rate, and it will be cleaned by Travis amplification later. So we have a spontaneous process which generates two photons. They travel via fiber, standard optical fiber, towards users, and users make measurement of polarization. So they randomly decide which state to measure, vertical, horizontal, or diagonal, which basis to measure, vertical, horizontal, or diagonal, anti-diagonal. And that's how it looks. So during last 3 years, we made a progress from a corner of optical table with pump laser optical crystals to this very beautiful and compact assembly, and it's integrated into the entangled state source, which not only generates photons but also performs of polarization compensation in the optical line. And we have pretty good contrast. This blue, orange, and red lines shows that if you scan polarization, you see that vertical and horizontal are very well orthogonal, and diagonal and anti-diagonal non-orthogonal, maximally non-orthogonal. So inside this box, you will see this two-pass structure on the top of the picture. So we first put a pump light, spread it into two parallel beams, and it goes through periodically poled KTP or lithium niobate crystal. And in this crystal, pairs of photons are generated, but we don't know where it was generated on a higher or on a lower path, and then we recombine two paths. But before recombining, we rotate polarization of one state, and that means that the fact that we don't know where photon was generated converts in the fact that we don't know and nature don't know the polarization, and that's a superposition called HH plus VV. And as soon as there are two particles and we can split it by wavelengths, that converts into entanglement between two particles. And here is the whole system assembled together. So the purple one is in the box entangled state source, and the white one are user devices. So that the entangled state source has two outputs, and user devices has one input each. Is they're measuring photons actually they're following like PBM92 protocol, so they're doing the same measurement as in PB84, but instead of comparing basis of preparation and measurement, they compare basis of two measurements. And if bases are coinciding, they have correlated. And then we use so-called ETSI-14 protocol that's already standardized protocol for quantum uploading quantum keys to user devices. Here you see the Fortinet devices, but not only Fortinet L2, L3 encryptors are supporting, there are also ADV, Sienna, Nokia, Juniper, and number of other vendors are supporting this protocol. So that means that it's compatible to wide industry available solution. And we are following the best practices of international best practices. So we've built a test bed. We have a fiber loop line in the Masdar city, that's like innovation city in Abu Dhabi. And there are 48 cores, so we can configure different lengths of lines, and we have real deployed fiber. So that means that we can test our equipment 24/7. And what we are also proud of, that it was tested both on a test bed and on the early adopter clients, and right now more than 7 months it's fully operational. So it works really well. What's good about entangled state source? So many people can say, oh, but instead of 2 boxes in prepare and measure, you need 3 boxes. So that's maybe not economically efficient, but you can make a switch-based network. So entangled state source, you can be connected to an optical switch, which literally configures optical channels. So it is not as a telecom switch which makes measurements and laser pulsing, but instead it has MEMS equipment to physically connect inputs and outputs. It's like an old telephone lines, which you can see in old films, old movies, when a person calls to the operator and say, I need to be connected to a person with this address. And the telephone line is manually connecting between these two people. So here happens the same, but with an optical fiber. We can connect many users. Each of them will have only receiver, not a transmitter and receiver. And at this scale, this this network can be economically viable, and the good thing that entangled state source can be in untrusted environment. So that means that we can build a full mesh network any to any without making a trusted node like it was, let's say, it was in the description of the quantum networks before. And telecom operator can be this untrusted node, and it can literally sell photons to the users. So we made such experiments in our lab. We used two 10-kilometer connection lines. We have 3 nodes, 3 receivers, entangled state source, so 2 to 32 optical switch, and we have pretty good quantum bit error rates. Yeah, that's 10 to 10 kilometer has a little bit lower bit rate because there are longer some distance. But it's enough keys to feed enough encryptors. And if you look around the globe, there are many QKD solutions, but we are proud of that. On the market, there are no other entangled QKD solution with so large technology readiness level. And if you look at these devices, the argument of PSI and NSA about the cost of equipment is pretty important, because on the market, such pair of devices to connect to provide one connection on one line, it will cost you hundreds of thousands of dollars. So to overcome this problem, we decided to go with another concept. It is prepare and measure, but a cost-optimized transmitter. Receiver still can be expensive because it has single photon detectors, which is still complicated to make cost optimal. But one receiver can time share between many transmitters and can be the central trusted node. But the transmitters need to be very, very cost optimized. So we asked ourselves, how can we do? And the good thing is that in our center, we asked to not only to make very good publications, but also make technologies. And we found out that it's completely empty market niche. So everybody is competing on distance and key rate, but there is still no solution to connect end users to the nodes of existing quantum networks. And that limits a lot the scalability of quantum networks. So what we decided, so we don't compete with others on key rate and distance, but because one encryptor consumes very few key. Toshiba produces something like 300 kilobits per second of a key material. At the same time, the encryptor consumption is something like 3 bits per second on average. Let's say 10G encryptor, which is usually used by an office where like 10 to 20 people are working, consumes 1 to 156-bit key per 1 or 2 minutes. So we can completely redesign system. And we decided to go with prepare and measure system, but we looked inside the systems and found out that in most QKD system, what we have first of all high volume, high speed quantum random number generator. And then we use quantum random numbers to modulate light at a high speed. We decided to completely go away from this concept and to go with so-called passive state preparation, where we unify the current quantum random number generator and state preparation. So we use a gain switch laser to prepare random phase states, which is very popular in QRNG. So Spanish QSide has commercialized QRNG based on it. My former startup Curate also used this random phase states to generate quantum randomness. But at the same time, this time beam qubits with some random phase, it's a qubit which is used by Toshiba, but they prepare only one of four states of delta phi. We prepare the full equator of Bloch sphere. So our phase is completely random from 0 to 2 pi. But we need only four. Remember, in BB84 protocol, we need four states. So what we can do, we can measure this classical state and post-select only events where our state is prepared to at the target states. At this point, you see that we have classical state. It's high amplitude pulses, but the phase difference is truly quantum random. So what we do, we split small fraction and set it to quantum channel, and the rest we send to tomography. And tomography is a real challenge, because if you try to measure it with an interferometer, it can distinguish only two states, 0 and pi. But interferometer completely do not know was it prepared power 2 or 3 power 2. That's a big problem. If you make two interferometers, there will be a challenge to stabilize reference phase difference between them. So what we can do, we can convert phase to polarization. So instead of beam splitter on the output of interferometer, we use a polarization beam splitter. And inside a fiber, early and late pulses are combined in the same time, but in different polarization domain. And that will allow us to make a polarization. But remember that we wanted to make a very well cost-optimized device. And for that, we use not a two beam splitters, but one beam splitter, but organize it in a loop. And the first pulse enters the loop, makes a loop, and goes into the same beam splitter when second pulse arrives. And with this middle pulse has early plus late. And zero phase converts to anti-diagonal state, pi phase to diagonal, pi over 2 to circular, 3 pi over 2 to counter-circular. So there are four polarization states, mutual non-orthogonal. Here in the picture, you see this projection system which can distinguish between these four states. So we can make local tomography, and we can post-select regions on the diagram where states are accepted as BB84 states, and all outside we just discard. So there are like either small amplitude on measurements or high amplitude on measurements. And that's how it looks in total. So we have a tomography device, we have laser with producing pairs of pulses, we have quantum channel of 10 kilometers, and we have a receiver which just measures the quantum states and detection. And here is once again Bloch sphere with diagram of post-selected states. And we made a proof of concept. We demonstrated it up to 2 kilometers of up to 10 kilometers of deployed fiber. The key rate, even at 1.5 megahertz state preparation rate, is still enough to feed an encryptor. At the same time, we are working on the next generation, which will prepare states with 100 megahertz repetition rate, and will allow to time share of the receiver with many transmitter and still provide enough key. So once again, like we're developing focused on this last node solution with time multiplex on one receiver, and we focus to integrate it with existing quantum networks or quantum networks which are building in the future. And we are looking for partners in different countries with whom we can commercialize the technology. So we expect that in the first half of 2006, we will be testing it with potential clients. So a few words about satellite QKD. If we want to go connect distant regions, so the good example is like China, they have a backbone node, and they have some distant areas where fiber do not go, or you can want to connect clients in different countries. I don't know, UAE and Europe, or UAE and any other country in the world. So in this case, you not always have fiber, and fiber can, even if fiber exists, the trusted node can go through different countries, so it's no-go solution. That's why quantum satellite concept is used. So satellite is a trusted node, but it's only one trusted node. So it flies over one station and exchanges KA, then it flies over a second station and changes KB, and then encrypt one key with another, and both stations have key A. And then they can make a common key to generate it. We also plan to use different satellites, because imagine that if UAE do not have own quantum satellite, but we can use one quantum satellite from Singapore, one quantum satellite from Germany, and in this case, if we connect, let's say, UAE and, for example, Australia, like some distant country, we need some source of trust. What we do, we combine keys from two different satellites, and then it can be double trusted. So that's how it works. One channel, another channel. Yeah. Actually, yeah, that's correct region now. And yeah, we have double keys. Yeah. And we have secure communication channel. So we don't have our quantum satellite, but we have our quantum optical ground station, which is focused to receive quantum keys from different satellites. That's a measurement device which performs polarization BB84 protocol and can work with as many quantum satellites as possible. And we want to support even more quantum satellites in the future. Yeah, and we also want that, like, ground stations alone are not useful, so we plan to integrate it in our quantum network, which is under construction. So what you see in the picture is a concept future, but it will allow us, if we connect our ground station to Masdar City and then Masdar City to Zayed port, then we can use the quantum keys to protect solutions for logistics, especially for, let's say, ships which are traveling in the sea for a long time, and they can upload quantum keys in the port and then use it for secure communication during going from one port to another. Thank you very much, and I think it's exact time to go for questions.
Thank you very much, Dr. Kurochkin. It's very comprehensive and nice presentation. All question in the chat box. Allow me to read the question. First question is from Research Center of Quantum Physics. I think it's Mr. Hamza. In the real-world context of QKD, what is the physical form of the eavesdropper, and how they carry out their attack?
Okay, so in the real world, so let me go back to. So we have an eavesdropper concept who has unlimited like capabilities, including replacing quantum channel, lossy quantum channel of lossless. So of course, this concept is hard to imagine in real life, but for example, in my experience, like the first deployment, real deployment I made in 2017 was between two bank offices, and the line was 25 kilometers. But the line was not just straight brand new optical fiber. It was actually, we asked telecom operator to connect us a dark fiber between two offices. So what telecom operator did, they connected 6 segments underground with patch cords and 2 segments in a building, so 8 segments in total, between 2 data rooms. And the total loss, nevertheless, like 25 kilometers should be something like 0.2 dB per kilometer. So it should be 5 dB loss. But it was but it was 14 dB loss because we had a lot of loss in between. And the route of a fiber was not straight. It was going in the city like in some crazy shape because it goes where like conduits are existing. But the line of sight between two offices was 7 kilometers. So that means that if one will replace with line of sight fiber, this channel, with brand new ultra low loss fiber, which has 0.16 dB per kilometer, it will allow to be around 1 dB in total. So almost all loss was present in a quantum channel could be converted into eavesdropper advantage by replacing a quantum channel with just very good fiber. That's point number one. But what else can be done? So that's then all this loss can be taken out by a beam splitter and measured actually. So and this beam splitter can be some active device. It can like make an active decisions. So if you make a consistent measurement, then you can like inject some light back into the channel. If inconsistent, then you can don't do anything. So that's an example. So the prepare and measure attack which is described here is very easy to do. So that's like when you make a total attack. Of course, this ideal quantum attack is much harder to do because it requires more sophisticated. But the group in University of Geneva has demonstrated that they used instead of intercept resent, they used an amplification media, very high quality optical amplifier, and they managed to be above this intercept resent line, but a little bit below red line. So today's technologies allow you to go pretty close. So when I said an atom, it can be some like an amplification media. Like it's not an atom, can be not an atom in vacuum. It can be atomic doped fiber, which converts one photon into 2 photons. But of course, it makes it with noise. So that's why we will see errors on the receiver. So extracting information to another photon, we affect an initial photon. And so the red line, which is a theoretical upper bound, which if you use ideal equipment, which can do anything not protected by laws of physics, of course, very hard to reach, but today's telecom equipment can go very close to this line. So yeah, so a quantum copy machine is actually amplifier, and spontaneous emission will inevitably affect and yeah, all amplifiers has noise.
Well, follow-up question. So in the future, do you think this quantum communication will be conducted using existing fiber optic line, or we should make a new private line, something like that?
So right now we are using existing
Mm.
lines because
So for completely to secure that, so we have to make it private line, or is
no,
there
like
no?
the model of security of QKD, and that's
Mm.
very good property, is that your photons are going through completely untrusted environment. It's
Mm.
so your fiber, like deployed somewhere, can be changed by somebody. Somebody can
Mm.
taper a fiber, so it's very easy. Like you just
Mm.
bend a little bit fiber, and light goes out. So classical information is very easy to extract from a fiber. That's why
Mm.
the model of QKD supposes that it's very paranoid. You know that your single photon detectors are noisy, but
Yes.
all errors occurred even from noise of your single photon detectors are considered to be actions of an eavesdropper. So that's why in our results, so like yeah, so even let me show here. Yeah, so here in this experiment, we like there is no eavesdropper on our line. There is no point to put much investment into attacking our research testbed, but there is still quantum bit error rate, which is 2.8, 4.9%. What we do, we don't say that, oh, we have our equipment naturally has this level of noise, let's consider attack only above this. No, we say in our like paranoid model, this is the 4.9% is all eavesdroppers action. So we always supposed to be eavesdropper on the line. We always suppose a quantum channel to be untrusted. And then we put a hash function, the so-called privacy amplification, to reduce amount of information in our key to have to eliminate this eavesdroppers information.
So
So
this secret key rate is already eliminated the error.
yes, that's
Oh,
actually
okay.
the gap. It's already actually the gap between the red and black lines.
Oh, okay.
That's why it's very important to do the optical production of your QKD device in a very high quality mode, because all errors are reducing your secret key rate because they are considered to be an action of eavesdropper. Of course, the dedicatedly deployed fiber is always good, because you can ask, if it's a new fiber, you can ask, oh, please put us an ultra low loss fibers to have better conditions, to have lower loss.
But it's not practical.
In most cases, yeah, in most cases, you have to use what is already deployed.
Yeah.
And between data centers, there are a lot of dark fiber. So if you're connecting two data centers, it's definitely a good use case.
Okay, thank you. I think we move on to the next question. Also, the participant can raise your hand to ask directly. Yeah, but we have another question in the chat box. In practice, is the secure key generation by the KQD, for example, BB84, permanently secure one established, or does it need to be redistributed periodically? Also, is the key sufficient by itself to encrypt data, or do we still need to use a classical encryption method based on the generated key?
Okay, so good. There are two questions. So the good advantage of QKD is that it's forward secure. So that means if you generate it in a secure way now, and let's say you don't use this key, or like you use this key to encrypt data, and somebody like had an opportunity to monitor your to copy all your classical data encrypted, it's impossible to attack it retrospectively, especially because the quantum part is happening with real physical photons. So for example, with post-quantum cryptography, it's believed to be secure now and secure against short algorithms. But if somewhere in the future there will be powerful enough computer to break the key agreement, then the stored key agreement protocol, because like it happens classically, can be attacked retrospectively. So that's a very big advantage of QKD. So because it's intrinsically forward secure. So what about the keys? It's like redistribution and all the rest. So in ideal case, you need to use your key in a so-called one-time pad mode. So that's when your a number of bits in a key and a number of bits of sending information is the same, and you use every bit of the key only once, and you use bitwise XOR. That's also information theoretically secure protocol. But right now, up to my knowledge, in business applications, nobody uses OTP. People uses symmetric encryption. It's like a lot of like mixing, and so in this protocols, the initial key, of course, reused. So there is a key derivation function from initial entropy of the key that's produced more entropy and then encrypted. Of course, the use of a smaller keys compared to send amount of information is a source of vulnerability. That's why we need to keep a limited amount of information sent by one key. That's why, for example, the encryptors usually asking for one fresh key every 1 or 2 minutes. So yes, you cannot use one quantum key forever. You need to recheck it, to change it. But if you compare to prior practices, very often these keys could be changed once a year, once like a half year or several years. Now it's changed once per minute. That's a scale of improving of your security. So if I would be asked how to quantify this amount, like priorly you could use like manual refreshing keys, like or pre-uploading keys in the equipment once it produced or once a year, Now it's once a minute. That's a scale of improvement.
Okay, thank you. I think it's answered the
Joga,
question.
there is
Yes.
something with your microphone. Yeah, now I hear you better.
Oh, sorry. Yeah. Yeah. Let's move to the next question from Mr. Hamza. Thank you for the great talk. Can you repeat again how to extract the randomness from the laser pulse?
So that's
yeah.
okay. So how quantum random number generators are usually working? I will give it on the example of quantum random number generator I made. So we produce two independent laser pulses in gain switch mode. The phase between them, phase difference, is random. It's important to make these pulses properly, so you empty the resonator from carriers to avoid phase correlations. But if you make this, if you make it properly, it works. So you see the proper diagram. You see the diagram on the interference. So, for example, you make imbalanced Mach-Zehnder interferometer. On picture on the right, there is a beam splitter and two arms, like one short, one long. And this, you see these periodic pulses, and it will make it interfere with one step. So pulse number one, 0 interfere with pulse number one, pulse number one interfere with pulse number two. And what we see the outcome of the interference, like 0 versus 1. The output on the interferometer port power of our measured depends on the phase difference. So that's a classical interference. And if you build the histogram of the output, so on the horizontal there is a measured power in arbitrary units, and on the vertical it's a probability to get output. You will see this. Some people call it like croissant or Batman, like which shape histogram. And very simple randomness extraction. You can say, okay, so I put an output, a comparator on the output, and if the measurement outcome is larger than some value, it's logical 1. If it's lower, it's logical 0. If you follow up by email, I think I can send some papers on this topic. And what we do in our case, so we produce these states, and this actually in one such state there are a lot of randomness, because it takes not like between two possible states, but it can take any possible states on the 2 pi circle, or maybe this picture is better. So yeah, so the phase difference can be some region around 0 phase difference, around phi, around pi, around pi over 2, or 3 pi over 2. And what we need, we can measure the phase difference and post-select the states. So we do the same like in BB84. You need to toss a coin or use separate quantum random number generator to generate classical random numbers, and then prepare the state. What we do in our passive state preparation scheme, we prepare a random state which can be anywhere on the circle, and then look where it is, and if it gets in one of these 4 regions, we consider it successfully prepared, and we know what is prepared. If it was not successfully prepared, we just discard. As remember, in quantum key distribution, we are not sending useful information. We are sending random bit key. And it's very important. If it was attacked on the way, we just discard it. We didn't lose any useful information. And only if we make sure that the key is secure, we use it for practical applications.
Oh. I have a follow-up question. Is it the same with the continuous variable? The procedure is same with the continuous variable, the squeeze state of photon. I think they also use the
Okay.
continuous variable.
In entangled states, you can use discrete variable and continuous variables. In continuous variables, you can generate two-mode squeeze states and then measure it, but measure it not with single photon detectors, but with so-called homodyne detectors. I have been working on continuous variables for 2 years. It's another beautiful area. Or you can make prepare and measure continuous variable.
What is the pros and cons between CV and pulse laser?
Okay, so the very good thing about continuous variable QKD is that it's much easier to combine the quantum signal with a classical signal, because a homodyne detector is sensitive only to very narrow line widths. If you try to do the same in discrete variables, you need to make like a cascade filtering, which is practically a complicated task, because actually if you cascade filters, their isolation do not sum up, but it's very challenging to filter out single photons. But in continuous variables, the homodyne detectors work the same way as a radio works. So you tune the local oscillator, and it finds the signal. At the same time, it's very challenging to make so-called local oscillator. So you have laser at the transmitter, you have laser at the receiver, and you need to and the wavelengths can be slightly different. Let's say it's different, just I don't know, 500 megahertz, which is in optics easy to happen. But that means that your reference frame between these two lasers is rotating with 500 megahertz speed. And in classical communications, all bits sent are multi-photon. So people have learned to compensate this rotation of reference frame, just monitoring and post-compensating digitally, and see this star diagram, this PQ, and there's these dots on the regions. With quantum, it's much harder, because all your signals they're very close to the origin of the coordinates. And to do this, people send the so-called pilot tone signal. So apart from quantum, which is very weak, which is like this, less than 1 photon amplitude, they have like strong pilot tone signal. But pilot tone signal is happening at the same wavelengths as your as your quantum signal. And it's very hard to isolate, because as soon as it's traveling via fiber, there are some, let's say, patch cords, and patch cords has reflections. So apart from clean pilot tone, you see also a lot of like weak reflections of pilot tone. And these weak reflections start overlapping with quantum signal. So up to my knowledge, only Huawei in Munich managed to make a CVQKD which operates at long distance, because Huawei has incredible experience in this coherent communication. Other startups like Lux Quanta or Australian Quintessence Labs, they're still challenging to stabilize this local oscillator and to send both significant piloton and quantum signal over long distances. So that's why right now distance is limited. So there are efficient post-processing algorithms. You also need huge computational power for post-processing. There is non-trivial privacy amplification for the coherent communication. But for the short distances, coherent QKD can produce larger key rates than discrete variables, and it can operate on light fiber very well because of this natural filtering.
Maybe we move to last question in the chat box. We have 1 minute. We know that using quantum infrastructure can be very costly. To address this, several studies have proposed a semi-quantum key distribution, where, for instance, the user operates with classical or modern device and perform only classical measurement, while the server utilizes a quantum infrastructure. Could you elaborate on what semi-quantum key distribution is?
Semi-quantum. Okay, like I have to admit that I don't know. So I didn't study I didn't make a deep study on semi-quantum. I know of one company, Terra Quantum, who is using. So I would say that they have marketing problems. So they say that they're doing QKD, but their amplitudes of the signal sounds like hundreds of photons. And they monitor quantum channel with constant reflectometry and try to measure any presence of a beam splitter on the way. So in cryptography, it's closer to so-called steganography, when you hide your information. So I would say that it's not classical cryptography, not PQC, and it doesn't fit what people consider to call QKD, quantum key distribution. It's some alternative solution that's like quantum protection by channel monitoring. So that's this approach I know is done by Terra Quantum. I believe that this approach should have its own niche. So, for example, for some applications, people don't want to use PQC. They think that their use cases are less time secure than QKD, and they want some in between and long distance. And they can use this approach, which is, let's say, monitoring quantum channels. So maybe I mean, under like in this question, this mentioned. So I know this. So also for satellites, QKD, some people say we can monitor quantum channel, like look in the sky and try to see that nobody's in the beam, and try to increase a little bit light power because we can put some limits. But in all these regions, we go away from information theoretical proofs. So both for this like channel monitoring and for all this like channel monitoring, like non-quantum, the advantage of QKD is that it has strict mathematical proof that if you follow these conditions, if you make your protocol in correct way, you will have so-called, okay, epsilon secure protocol. So you can put the epsilon parameter with a like probability of guess of your key, and you can make this epsilon arbitrarily small. Let's say usually people make it 10 to the power minus 10, but you can sacrifice more key and go in 10 to the power minus 20. So it depends on your request. So that's a correct, proven mathematical claim. So with semi-quantum, you have claims like that's impossible because it's very hard, because it's too hard. But then the main question is how to quantify this word too hard. What is too hard and what is not too hard? Because like, let's say this quantum attack, quantum copy, it's too hard. But at the same time, if you take very good optical amplifier, it can go very close to ideal quantum copy, to like low noiseless quantum machine, because today's telecom equipment is very good. That's why that's a big gap between like PQC and QKD. If you want something like practical and working on your mobile phone, that the PQC is what you need to go. If you want a mathematical proven solution, like that's only QKD which is available now.
Okay. Thank you so much for your nice answer. Uh, 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 I would like to. That is the last question, I think. But I would like to give some information. I don't know you already know it or not. We here in Research Center of Quantum Physics in Indonesia, we start to build a quantum optic laboratory. We will make the QKD based on the Ecker 91. So
Fantastic.
yeah,
Fantastic.
we now in the States to build the system. And if we have question, is it okay if we reach to you?
Yeah. I believe that if the science should be done in communication, science should be global, and it's very important to visit to see each other both on the conferences and on lab visits. So, for example, in November, it's still not announced, but in November there will be called CyberQ conference, and you can visit Abu Dhabi and see. Also, yeah, I'm personally love to visit different groups and labs in person, and if I'll be nearby, I'll try to maybe also visit your labs.
Thank you so much. So that is mark our the end of the colloquium. Thank you so much once again for our speaker, and thank you for all the participants who joined until the last. And have a nice day. See you again.
Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you. Bye.
Bye.
Bye.